Okay. Just caught somebody, Nicole. Anyone else? Okay. Okay, let me know if, I think somebody just came online. Let me see if I can find them. If I haven't given you permission to record yet, please let me know. Alondra, I just got you. Alondra, do you need a permission number to get in? Are you officially enrolled? I'm not sure. I don't hear her. Alondra, can you hear me?
Yes, I can.
Good. Are you officially enrolled or do you need a permission number?
I think I'm gonna need a permission number because
Okay.
I think I'm still on the wait list.
Yeah, that's what I thought too. So I'll try to send you that later today.
Okay, thank you.
Anyone, I don't think there's anyone else. Is there any?
Yeah. Can I get permission?
Oh,
It's Chris.
sure.
Thank you.
Find you though. There you are.
Thank you.
You got it. Anyone else need permission to record? Is there anyone else trying to add the class?
Professor, I need permission to record.
Permission to record. You are. I'm having trouble finding you on my list. Whoa, it's blowing where I am. Pretty windy. There you are. I think you have it now. Anyone else? Great. Okay, well, welcome back. A couple things to get into. Okay, as soon as I start here, I've got someone outside with a, oh, that's sort of interesting. I was going to say they have a, what do they call it? Leaf blower or something. I don't know how that's going to work in the wind, but I know it's going to make a little noise. So if you hear a little background noise, it should go away in a minute or two. Hopefully you can all hear me. Some announcements. Normally I have an office hour right after class. Today I will not be able to meet that obligation. I have a committee meeting in our department, so I won't be able to stay right after class. However, I'm not sure how long that committee meeting will last. So what I'll probably do is try to re-invite this class after that committee meeting. When would that be? Well, the committee meeting might go from noon to 1. That would be the longest it could go. So I could be inviting you at 1. If you can't come, I totally understand it. It's not the normal office hour. Just, I guess, ignore the invitation. But if you are able to come, just re-sign in and we'll have an office hour at 1 or maybe sooner if my committee meeting ends sooner. That's just for today. Okay, normally I'll be able to stay after class. That's one thing. The other thing is I tried something on Canvas that I haven't done before. I tried to set up a place for you to submit your homework for week 1. And I'm not sure it's going to work, but it looks like it might. So if you go online, you don't have to do it now. You can do it after class when I normally would have the office hour. That might be convenient because I want to see if you're able to do it. So I'm trying to see if you're able to upload your homework into Canvas where it says homework week 1 under this class. And if it works, then we may use that in the future. If it doesn't work, then I'll do something different next week. So try to upload your homework sometime today. Could be right after class. It could be later today. And you probably will know whether it's working before I will, but in any case, try to do that. Any questions about both announcements? Once again, I won't be meeting right after class today because I have a conflict with a committee meeting.
So a student just messaged saying that the assignment is locked and it won't open until the 31st of January.
Oh. That's interesting. Okay, so it's not working. I don't know why it won't work until that time, maybe because I don't lock it. You might have another person or two try just to see if you get the same message, but if you do, don't worry about it. Just hang on to your homework. Okay. We'll try to, well, the 31st of January is what, Monday? So that's not such a big deal either. Okay, thanks for that info.
I have a question. Is today's homework due today or would it be for the next Friday?
Today's homework would be due today. The homework that I signed on Wednesday, is that what you're asking about, I assume?
No, the homework you sign on Fridays.
Oh, the seminar, no, that would be due the following week.
Thank you.
Yeah. Okay. Any other questions? Okay, well, since I'm not having my usual office hour, maybe I'll take a couple minutes out now to see if you do have any questions on the homework that was assigned. So let me flip my mouse around here. Get my furniture in position.
I know in office hours, we covered an example of how to write out a plane. Maybe we could do that first.
That would be good. That'd be a fine idea. Yeah. So let me get my OneNote up and running, and we can talk a little more about that. Okay. Okay, I hope you can see my OneNote, and this is not our class, but we're making progress toward our class. Let me see where our class might be. Some of this is okay.
We're looking at one of the faces of like that pyramid thing.
Yeah.
Look at planes.
Yeah, but I think I had it written. I think it might be on the next slide. So let me see if we did that here. Yeah, it doesn't look like we did it here. So let me check the next slide. This is still lines. So maybe the one after. On that one. This looks more like it. Well, okay, this may be what I did in the other class, but it might be an okay review. Let me see. So there's a couple of ways to do planes depending on how the questions are posed. Okay, so I think this was, now that I'm situated here, I think it was something else. Hang on a second. Yeah, so this would be an example. So here's the figure that the student just mentioned, this sort of slanted pyramid. And we had these vectors. So the vector going from the point up here on the z-axis at 3 down to the point over here was called u, and the coordinates of it were where you go down 3, you go in the x direction 2 and the y direction 3. So these are the numerical values of that vector. And this vector back here labeled as v is going down 3, and it's not moving at all in the x direction. So that's why there's a 0 there, and then it's 3 units over. Let's see, is that wrong? No, that's right, 3 units over in the y direction. So these two vectors, u and v, both entirely lie within the plane that we're after. We're trying to find the plane, which is denoted here as plane 1. And so using this equation, what we do is take s times u, which was 2, 3 minus 1, plus t times v. And then we need a vector that gets us up to the plane. In this case, it was just 0, 0, 3. So this is one example of how to do or how to find the vector equation of a plane that's presented in front of you. Now that's not quite like the homework, so I may switch to the homework, but before switching to the homework, are there any questions on this one? It's an illustration of this equation here. So these are called a linear combination of the vectors u and v as s and t vary. Those are the parameters. And d, I'm calling the displacement, which just carries me up to the plane. Let's see if I turned the page and did something like the homework. So yes, so this would be more like the homework. So the homework that I assigned from the book asked if you had a plane that had these points on it, and what would be the equation of the plane. And so this is similar to the last one, but yet different enough to go over again. So what we did in this case was to change these points to vectors, and then our text that doesn't look very different. I mean, we use the same notation, but now we think of these as vectors v1, v2, and v3. And so I didn't have a picture of the plane in front of me, so I made sort of a general plane here. I'm not sure that the plane that we're after looks like this, but the picture is a guide or a helping device, not necessarily meant to be the real picture of the plane. So each of these vectors now can be thought of as going from the origin up to the plane, v1, v2, and v3. And you still want to use this equation. That's the equation that is being presented in the book at this stage. So you need two vectors in the plane. And I said one way to do that would be to take v1 and v2 and find the third side of that triangle, which is either pointing this way or the other way, and call that u, because whichever way it's pointing, it's a vector that lies in the plane. So in this case, u turned out to be the vector difference of these two vectors, which was this. And then we needed another vector in the plane, and for that, I chose v to be v3 minus v1. v3 is over here and v1 is here, so v would be pictured as the third side of the triangle, since those are tail to tail to begin with. And we formed v in that manner, which turned out to be this. And now we have two vectors that lie entirely in the plane, the u and the v. So we substitute that into the basic equation, which I did here. And the only other thing I needed was a vector that went from the origin up to the plane, and that could either be v1, v2, or v3. I chose v1 again, but it could have been any of the three. So this turns out to be the vector equation of the plane described, and I assume this is problem 3, part A, I'm guessing, or maybe part B, I'm not sure. One of the problems in problem 3 in the book. Afterwards, you could ask questions like, if you're given a vector, are you on the plane or not? And you can try to see if there's an S and a T. S and T could be any number of real numbers that are equal to the given vector. And if there are S and T that work, then the vector is on the plane. If there aren't, then it's not on the plane. Okay, so I think that's a reasonable review of what we did in class Wednesday. Any questions?
Does it matter what you chose your U and V to be?
No, in terms of there are different choices. So I chose U to be this vector difference here. I could have chosen U to be this vector difference, or V3 minus V2, which didn't come into play to this. But pictorially, you're trying to find two vectors that lie in the plane, as this picture sort of shows. And it doesn't matter really how you get it or which ones you take the difference of. So there are a lot of vectors that can serve as vectors U and V. In this problem, you had to find them. The previous problem, it was pretty clear because you were given vectors U and V that were already in the lied in the plane. Other questions? Well, why don't we leave it there? And if anyone wants to go over some of the other homework problems, I'll try to catch you after my meeting today. And if not, there's always Monday. And there's also the other section. I don't know. Let me see if I have the enrollment sheet. I'm not going to take roll today. Got my background noise again. Hold on. So are there any other students who would like to be added to the mailing list for section 2? And today is a good illustration why you might want to do that, because section 2, I am having my office hour right after class, and you'd be able to enter it right at that time. So let me just ask again, are there people who would like to be added to the mailing list of my 4190 section 2? If so, please let me know right now.
I would like to be added.
Your name?
Andy? I was the one with the long last name last time.
I'm sorry, I didn't even catch the other name. Say it again.
Oh, the last name was Cardenas Maciel. Andrew.
How about your first name?
Andrew.
Well, I'm striking out. I'm going through the list. Oh, no. I'm sorry. Spell your first name.
Andrew.
Okay. I do have her last name, Traub.
Last name is Cardenas, like the store.
I'm sorry. Give me the first two letters.
C-A-R.
No. B-A-R.
C. Like cat.
Got it. Got it. Okay. Thank you. Took a while, but I got it. Mailing list. Anyone else? You're welcome. I'll do that hopefully later today. Anyone else like to be added to the mailing list of the other class?
Could you add Seth?
I can add Seth, as long as I can find Seth. Yeah. Seth, what's your last name?
Godino?
Gotcha. Good enough. Thank you. Anyone else?
Professor,
Yes.
I'm from the afternoon class. I just came today because I don't think I can make it to the afternoon class. I didn't know if you wanted me to tell you because when you take roll later.
I'm not going to be taking roll, but I appreciate you bringing it up. It shouldn't be a problem.
Okay, thank you.
Sorry that you're here and I can't do the office hour with you, but that just happened. Anyone else?
It's okay, thank you.
Anyone else wish to be added to the afternoon mailing list?
Could I be added? Lynn?
Okay, yes. That was LYNN, I assume.
Yes.
I will add you later. Anyone else? And by the way, nothing's special about today. You can do it another time, but if you wanted today, you would have the office hour, right? That's the point. In fact, you can just come to the office hour if you wanted to. Okay, I'll let it go at that. So let's get back to what we're doing. So where we're at is really moving on to the second section. And the second section is on vector spaces in general. So let's turn the page here. Let me go forward. Let's see where I am. Yeah, I'll just go up to the end here. Page, that'll work. Okay, so you have your book. I would open it or have the e-version open, whatever you have. And section 2 has a list of assumptions on page 7. And they're important enough that we need to list them out. So this is the definition of a vector space in general. It's an abstract definition. So far, we've done vectors in terms of geometric, how they look as arrows and how you can add and scalar multiply them in that way. And we've recently done vectors as numbers, either in the plane or in space, and how to find equations of lines and planes. But now take a look on page 6. Here's what it says. A vector space, also called the linear space V over a field, and they tell you fields are discussed in the appendix C, consists of a set on which two operations, addition and scalar multiplication, respectively, are defined, so that for each pair of elements x and y and v, there is a unique element x plus y and v. And for each element A and F is the field, and each element X and V, there's a unique element AX and V such that the following conditions hold. And then they give you VS, which is vector space, condition 1, 2, 3, 4, 5, 6, 7, 8. And that's where we start. Okay, so this is a quite general definition. So let me write it out. General definition. A vector space. And in the book, it's on page 6 and 7. And what it says, I've read it out loud, but I'll give you the highlights, I suppose. The vector space is denoted as V. So V is called the vector space. And it's understood you have something that they're referring to as F, which stands for field. And, well, first of all, do you know what a field is? Field is something that you learned from middle school or high school many long time ago, and there are what field conditions. And well, I guess it makes sense to go over what a field is first of all. So a field is a collection of what usually called numbers that that meet collection of numbers that satisfy the field axioms for the operations of addition and multiplication. So what are they? Well, field axiom 1 would be that if you added two numbers together, if A and B were both in the field, then so is their sum. This is called closure under addition. And at this point, it probably makes sense to think of just normal numbers, real numbers. Real numbers form a field. Field axiom 2 would be that A plus B equals B plus A for all A and B and F. That's the commutative property. Of addition. And hopefully now you start to see that you've seen these before. Field axiom 3 has to do with A plus B plus C. If you add these two first and then add the result of C, you get the same thing. And if you add B and C first, parentheses tells you what to do first. And this is true for all A, B, C, F. And it's the associative property. Of addition. Field axiom 4 says what? It says there exists, you know, say this better. Say this better. For each an element of F. This be an element of F. Oh, no. Sorry. This one first. There is element of F of 0. Is that what? A plus 0 equals 0 plus A. For all elements. A and F. And this means there is an additive identity. And that additive identity is 0. So if you add 0 to anything, you just get the anything that you began with. And finally, field axiom 5 says what? And by the way, these are not even written in the book. So you probably, they're in the appendix, I'm sure. Field axiom 5 says for each A and F, there exists B and F such that what? Such that A and B is add up to 0, the identity, and B is usually written as minus A. So that's a customary way of doing that. And what is this saying? This is saying there are additive inverses. Okay. Well, unfortunately, or fortunately, these are half of the properties of being a field. So we're defining what it means to be a field before we get to even what a vector space is. But these should be familiar to you. So what are fields that you know? Fields you know. Would be the real numbers. It could be the complex numbers, if you're familiar with that. And also the rationals are not to be. If you take all fractions, you know, A over B, where A and B are integers and B is not 0, that turns out to be a field as well. And definitely the most common field that you know is the reals, all the real numbers. But the other two are also candidates. Well, this is only half the conditions. All of these conditions, F1 through F5, go over for the operation of multiplication. So the easiest way to think of this is just the normal real line with the usual addition and the usual multiplication. And so let me sort of go through the others a little more quickly. But they are, there's F6, which would say that A times B is in F when what? When A and B are in F. So if you multiply two numbers in F, its product is in there as well. And that's closure under multiplication. It's abbreviated multiplication. And F7 would say that A times B is B times A for all A and B and F. And that's community property of addition. Community property of addition. Whoops. Multiplication. We did addition already. Sorry. Right up here. So this is community property of multiplication. So it doesn't matter which way you multiply two numbers, you get the same thing. There's a community property of, there's an associative property of multiplication as well, which would say A times B times C is the same as doing A times B times C. And this has to hold for all A, B, and C elements of F. And that's the associative property of multiplication. What else? Oh, there's F9, 10. F9 says there's a multiplicative identity. Multiplicative identity. And what is that? And usually it's called 1, like the additive identity is called 0. And A times 1 is the same as 1 times A. And this holds for all A elements of F. So it's an element in F. 1 is an element in F. So that when you multiply it by any other element, well, you don't get anything new. You just get A. That's the multiplicative identity. And F10, multiplicative inverses. That says for all A and F, A not equal to 0, there exists B, should say for each A and F, A not 0, there exists a B, such that what? Such that A times B equals B times A equals 1. And B is usually called A inverse, and the big word is 1 over A in the usual sense. So that's talking about multiplicative inverses. And those are there are 11 of these properties altogether. And the last one connects the two operations. So it's the derivative property. Distributive property of multiplication, addition. And what does that say? That says something like this. If you multiply A times B plus C, you get A times B plus A times C. And this has to hold for all A, B, C, and F. Okay. Now, I've already said the way to think of this is in terms of properties that the real line has, the complex numbers have, and the rational numbers have. Some of you may have had the abstract algebra class 5170, and you may know that there are fields that are finite. So for example, some other fields that are around are the integers mod 2 or the integers mod 3. Integers mod any prime would be a field as well. So all of these properties would hold in those fields. If you don't know what they are, don't worry about it. You won't need it in here. At least I don't think you will, if at all, very, very little. But it's nice to know that these axioms are not just for the real line. There are numerous other fields around. The first three are the most common. I'm hoping all of this is stuff you've seen. And what's interesting is we're about to do the same thing for what a vector space is. So for fields, the primary example would be R, perhaps Q, which even preceded that. Historically, people knew fractions before they knew irrational numbers existed. And then more recently, acceptance of complex numbers turned out to be finally something people agreed to. But it didn't come overnight, that's for sure. So these are the most common fields. Any questions about the field axioms? I think these are things you would have seen maybe in middle school or high school, hopefully. But if you haven't, they're familiar properties, I'm sure. Let's do the same thing for the vector field, which is where I was going to start. Now, for most of the time in here, a vector field will be over, a vector space will be over a particular field. And most of the time, the field of choice will be this one. So most of the time in what follows, we'll be using that. But it could be something else. It could be C, it could be Q, it could be Z, mod P, any of these things. Let me flip the page. So now we're going back to the book. So we're describing the definition of a general vector space. And so the vector space is called V. It's a collection of objects. A vector space over a field F. And we've just reviewed what F is, what it means for F to be a field. So to have a vector space, it really just sort of extracts the things that we've been doing the last 2 days. So for a vector field, you basically need 2 operations, the operation of vector addition. So general vector field V over a general vector space V over a field F consists of a set of objects called vectors that have 2 basic operations. And the operations are called vector addition and scalar multiplication. And if you ask me, well, why didn't we include vector subtraction as well? Subtraction is usually can be thought of as adding the negative of a vector. So that sort of doesn't have to be added as a special list of properties, because subtraction can be thought of as adding the negative of the vector. Just like for a field, you don't go through all the axioms for subtraction either. So a vector field does have addition and multiplication. Now, it turns out it has different kinds of multiplication, but at this point, we're only fixing the definition to apply to scalar multiplication. So now, with this said, now we can go back to page 6 and 7 and write those out more carefully. Here are the conditions. So definition of a general, this is brief. Definition of a general vector space. Objects are called vectors that have 2 basic operations. That's fine. And satisfy the following conditions. vector space condition 1 would be, and vectors are usually denoted by x and y, or two vectors x and y in V. Yeah, you know. You know what I'm going to do? I'm going to enlarge their list because I don't see something I want to have in here. So I'm going to call it vector space condition 1. If x and y are in V, then so is the sum. So that would be closure under vector addition. I don't know why your book doesn't have that. Well, it says it above. It says for every x and y, the element x plus y is in V, but I'm just going to make it one of the properties. So I'm enlarging their list. Vector space condition 1 would be what they have, and that's that vector addition is commutative. So for x and y, any two vectors in V, x plus y equals y plus x. So vector addition is commutative, and certainly that property rings true in the examples that we've done this week. So the geometric examples of addition, it didn't matter what order you added the vectors, you got the same vector coming out. And the numerical examples that we've done this week, it doesn't matter because you just add the components, and it really comes down to the components are the elements in the field, and since it's commutative, so will the vector be. So, but if you want to, we can say it's commutative. What? Vector addition. Yes, 2 would be the associativity. Yeah. So again, this time there are 3 vectors, x, y, and z, all elements of the vector space V, x plus y plus z. If you group them this way, add these 2 first and then add it to that, you'll get the same vector if you do this first and then add it to the first element. And so that would be property. Addition, this would also be the associative property. And this holds for any x, y, z. It's not just a particular pair. So maybe I should say that for all, but for any. Vector property 3, and I added 0 to this list. So my list is a little different than theirs. There's an additive identity. So there exists vector 0. Be careful. This 0 is usually not the 0 in the field. Normally I'd put a little arrow over these things, but your book doesn't use that notation. But it is a vector, so it's an element of the vector space, okay? Such that what? Such that for all vectors in V, 0 plus x would be equal to x plus 0, which would be x. So if you add the vector 0 to any other vector, you leave the other vector unchanged. Okay, that's called the, again, the additive inverse, additive identity. What is the additive identity? It is the vector 0, because when you add it to anything else, it leaves it unchanged. And last is vector space property 4, which says now I'll just call it additive inverses. Which means what for each x in V there exists y such that x plus y is equal to the 0 vector, which is equal to y plus x. So there's another vector that you could add to the first vector that gets you back to the 0 vector. And that vector y would be called its additive inverse. Questions on vector properties 1 through 4. I included closure there. Okay, so this is just sort of documenting what we already know vectors do, but in the same process, it's generalizing it into a definition. Now, the remaining properties have to do with scalar multiplication. So let's put them down. So vector, I guess if I want to be consistent, maybe I would have a vector space property 5, which would be different than theirs, which would be what? Closure. So for each x in V and what? Now, what are they calling their scalars? They're calling them A, B, C, that's fine. And A in F, then what? A times X is in V. So here we think of A as being a scalar. That's calling it right. Yeah. Something. It's like scale. A is a scalar. And for any scalar times a vector, when you do that multiplication, you get a vector. I would call this closure again. Closure of scalar multiplication. Okay, so again, my list is going to be a little bit off from the one in the book because I've been emphasizing that when you multiply a vector by a scalar, you get back another vector always. So my list here, vector space 6 would be what? Going in their order would be their vector space 5, and it would say if you multiply any vector by 1 is in the field, x's in the vector space, we get back the same vector. So this holds for x of b. And again, one is the unit multiplicative one in the field. BS7. Says that when you scalar multiply, you can associate it as you want. So here's what this is saying, that if you multiply two scalars together and then multiply it by the vector, if you were to group things in this way, first multiply the two scalars together, that you would get the same thing as first multiplying the scalar by the vector and then multiplying that by the other scalar. So in that sense, it looks like associativity. Of scalar multiplication. It doesn't matter if you multiply the scalars first and then multiply them by the vector, or if you multiply the vector first by b and then multiply it by the second scalar a, you'll get the same result. So this would happen for what? For all a and b elements of the field and x element of the vector space. And by the way, I mean, in your mind, I hope you have more than just blindly reading this down. So if you had a vector that looked like the vector 1, 2, and you multiplied it by 5 and you multiplied it by 10, what is it saying? It's saying that if you first multiply these together, getting 50, and then did this, and how would you do this? You would just get 50 and 100. That you would get the same answer if you first multiplied the 5 times the 1, 2. In other words, you get 50 and 10. And then if you multiply that by 10, you'll still get the 50, 100. So these are the same. It doesn't matter if you multiply these two together first and then by that, or if you multiply this first by that and then by that, you still get the same thing. So each of these properties you should be able to at least verify for numerical vectors in R2 and R3. But this is codifying it. This is making this true for any vector space. What's left? Nothing more. Yes, 8, my list. And that says it's sort of a distributive property. So let's write down what it says. It says that if you have a scalar times the sum of two vectors, that's the same as saying the scalar times the first vector plus the scalar times the second vector. So it looks like a distributive property of scalar multiplication over addition. I would say it's the distributive property. Scalar multiplication over what? Vector addition. In other words, you could add these two vectors, and this has to hold for what? For all A and F, and all X and Y and B. So if you like, you can add the two vectors first and then multiply it by the scalar. And you'll get the same result if you multiply the first vector by the scalar and then multiply the second vector by the scalar and then add them together. So it has to do with order of operations again. And actually, I'm really happy, even though it's a little tedious, that I went through the axioms of fields first, because all of these are sort of mirrored in the axioms of fields. Last one, vector space axiom 9. I should be more than 9. I should have 10. So somehow my number is off in this one. Well, I'll look for it in a moment, but it's the mirror of this one, the last one. So instead of taking the addition of the vectors, take two scalars that are being added together. So we have A and B, two scalars, and then multiply that by X. You get the same thing as if you would multiply A times X plus what? B times X. Understood here that A and B are things in the field, and X is something in the vector space for all. Well, it's not just certain values, all of these. Again, this looks like a distributive property, but it's a little different than the other one here, because you're adding the scalars first and then multiplying by a vector. And you're saying that if you were to do it that way, you get the same thing by scalar multiplying by X and by Y, and then adding the results. So again, it has to do with the order of operations, but you could also say distributive property of, well, you've got to be careful on the description because it almost looks like this one. It's a distributive property in the sense that you can think of X times this and X times that. You can distribute the X times the sum, and here you're distributing the A times the sum. So you can think of a distributive property of vector scalar multiplication over this, but I don't think I'll write it out. Now, which one did I miss? Let's see.
You didn't
It's
miss.
missing the inverse, I believe.
Which one on their list? I don't have an inverse for this. Did I miss it?
You have all of them that are on their list, but you added the two closures, but the first one you called 0, which is why you're only one number.
Oh, which is why I'm on 9. So I didn't miss anything. Thank you so much. Okay. I have 10 as I should, but my number is started at 0 and ends at 9. So there's 2 more than they have. If you want to just have their list, just you can just say if you do what? If you add 2 vectors, you get another vector in the space. That's the closure. And the other closure property was what? If you scalar multiply a vector by a scalar, you'll always get something in the vector space. Actually, I'm happy I have those on the list. Questions about the list? Yeah, please.
What was your 6 called? Is that the multiplicative identity?
Let me see. So now I'm back here. It's like a multiplicative identity, but it's involving both different operations, right? So you're involving vectors, but you're multiplying it by a scalar. The scalar, that's the multiplicative identity in the field. So if you multiply by the one in the field, that doesn't change the vector. I wouldn't say it. Now, it's a little, well, let's quickly, I'm almost out of time here. What would be the examples? Okay, so if I had a little more time, certainly the examples would be vectors in R2, in R3. So we picture these as vectors that would look like A comma B, and picture these as vectors that look like A comma B comma C. And if you want to stay sort of in the mainstream, you could say that A, B, and C were elements of the real line. Okay, and so certainly the axioms or properties that we just went through hold for vectors that have two components or three components. And you can go through each of these properties and verify them. And so this would be your main example, I would say. So this would be the main example. What would be the next example? Rn. Oh, I guess I should say, you don't have to have R in here. You could have complex numbers. Or you could just have rational numbers. And the appearance would look the same. They would look like components, vectors that have components 2 or size 2 or size 3. Most of the time for us, we're going to be sticking with the field being this. So this is what F would be in the above description. How would vectors in here look like? They would look like, well, they'd have n components. So instead of doing AB or ABC, I probably would do A1, A2, all the way up to AN. Little harder to picture this in that we can't draw them as easily, but you can still see how it would work. You know how vector addition looks. So if you were to add a vector that looks like this to another vector that looks similar, what would the vector addition look like? It would just look like A1 plus B1 and A2 plus B2, all the way to the end, AN plus BN. So that's how vector addition would work in Rn, and how would scalar multiplication work in Rn. So if you wanted to call, so if you had a vector x that had components x1, x2, all the way up to xn, and you want to multiply it by a scalar, which they're using a, so x is in Rn. And if you pick a just to be some number in the reals, so a times x would look like this. And it would look like AX1, AX2, AXN. So this would be how scalar multiplication in Rn looks. Now the cool thing is, even though R2 and R3 are the ones you learn in calc, and it's not a big step up to Rn, even though you can't picture it as well. The cool thing is there are other examples. And I don't have time to go through it in detail, but at least I'll help you with the reading. The other examples include matrices, which we haven't got to yet, polynomials, and functions. And those are explained in the book. Now let me see how far I got. I knew this was going to take a long time because the choice is not to list these out at all, which is not a good choice, or to list them out exactly. And I chose to list them out exactly. Let me see. They show some of the examples that I just went through in example 1. But let me see if I can give you some homework. So how about this number 1 on page 13? So homework. Number 1 on page 13. Future homework. You want to get ahead since you have a weekend. It would be 2, 3, 4. So numbers 2, 3, 4 on page 13 again. Why didn't I put this in the current homework? Because I didn't get to matrices and I didn't get to some of the things in there. But I think you probably could read the book and do those problems anyway, if you have. So if you have time and interest in getting ahead, feel free to do problems 2, 3, and 4, which will be assigned Monday. On the other hand, if you just want to do where we are at, do number 1. Okay, I got to run because I got to go to this meeting, as I explained earlier. But look for an invitation. You might even try them in the meantime. Go through number 1 maybe, or try to look at some of the other examples. I will try to invite you after my committee meeting. The worst case would be around what? 1 o'clock, I guess. And maybe even earlier. Have a good weekend. Sorry I can't do the usual office hours, but hope to see you later. Bye.
Thank you, Professor.
Yeah,
Thank you, Professor.
you're very welcome.
Professor, so just to make sure, none of these are on the homework list due today, right?
That's
This is
correct. All
Okay.
of these would be collected next week.